Good, March.
Yeah.
Okay. So everybody turned in that worksheet A, right?
What?
Worksheet A, that was the one with the waves on it. We were talking about amplitude and period and cycle, right? Huh? You got worksheet A? I don't have the answer to it. I'm not even in my room. I can't. Then at the end of class, I was handing this one out.
Oh wait, no, you can't give up that. You get to pull it at the top. Oh wait, that's the
Guitar. You don't need it. This one here. So referring to the multicultural activity 8.1, did you read it?
I did.
What am I trying to get across?
Shorter things make different.
Well,
the longer they are, the deeper the sound.
does anybody know the actual name of this? What it's called?
Glockenspiel.
Very good. It's a glockenspiel, which I never took German, but I think it means what? Strike and sound or something like that,
Well, spiel means play.
right? And I'm very fortunate, I'm not much of a musician, but I can read off of here that C. So what's the relationship? This is a performing arts school. That's an octave. Yes. So what is the relationship between this bar C and this octave of C? Take a look at that multicultural activity 8.1.
They have the same degree.
That's D, so that's D. That's D. So if I measured this bar where the C is, and I went an octave up where the higher C is, what's the relationship between the length of those bars? 1/2. In actuality or theoretically? Who's had music theory? Yeah. In actuality or theoretically?
Okay, I guess you're saying theoretically.
Theoretically. Because what's going to happen here, we're going to take a look at a video later this bell. If you notice the bottom of these metal bars here. Are they flat?
No.
No. What's the shape?
They go like this?
Yeah, they're curved a little bit. In other words, just because something is a certain length, is it going to always produce the same note? No. What are the factors? Thickness. Any other factors?
Length.
Anybody want to play with this? So Jeremiah, you finished this handout already, correct?
I got halfway there. I'm at number 7. I picked up number 8.
So let's look at some of this theory. So you look at a guitar. Does the guitar have a C string? D, A, D, G, B, E, no, but let's say you tune it to a C, 16 inches long. Now you're kind of assuming that every string would be the same thickness. Is every string on a guitar the same thickness?
No.
No. Why not? So you can get different sounds. You want to come and demonstrate to the class?
She said that.
Come on in. One of the advantages of being in a performing arts school.
Get out.
Like a bird.
Then try to rap.
Do you use flat round or round wound? Round wound. If you know about guitars, there's different kinds of strings, correct? Different kinds of strings. So now, theoretically speaking, let's say you want to calculate the length of the D. The length of the D string. It's really difficult.
I can't be the only one who got that.
So, here's your C, 1/1. Here's your next octave C, 1/2. The D, if the tensioning was the same and the material was the same, kind of like a harp, the length of the D string would be 8/9. 8/9 of what? 8/9 of 16. So
14 and a 5th inch.
So now you grab your calculator, let me just start from a fresh screen here so you can see what's happening. So I'll go like this, I'll just be safe, I'll go parentheses 8 divided by 9, close parentheses, times 16, and you can do this without a calculator.
Yeah.
And that turns out to be 128/9, then you hit Control G, right, Control G to get the decimal.
I didn't get the decimal.
Oh, hang on, what's that? Here, I'll just hit Enter there, and then hit Control G. Oh, no, not Control G, Control Enter, what am I saying? I'm out of my help. 14.22222222. 14.222222. Do you see a problem with that?
It's in decimals.
It's a decimal. Does it ever stop?
No.
No. Does it ever repeat? Yeah, it repeats. So once you build that guitar or you build that harp and you make that string, is it now over?
No.
It's always perfectly going to be in tune.
No.
No. What happens?
It loosens out.
You've got a little tuning peg where you can increase the tension or decrease the tension to fine tune. Guitars, if they're made out of wood, they expand and contract with the weather. You have to be able to have that ability. How do they tune this glockenspiel?
They tighten the bolts.
How do they tune it? Is the bar perfectly flat? No. I don't want to take it apart. You see that curvature right there? In other words, to tune it, they have to shape it.
So eventually it just
Yeah, so they take a little bit off, a little bit off, a little bit off. What happens if you take too much off?
start over.
Or all over again.
Or use it to make it smaller at higher.
So you can go ahead and do those calculations on that. We can try to field some questions on that tomorrow.
So do you want us to find the decimal or the fraction?
Whatever you prefer. I kind of prefer the fraction. Yes, sir.
Yes, you're just only playing out there.
Ah, what's the frequency? Good point.
You can have
But,
Ah.
I got
This entire lesson is done. Hey! Okay, let's watch a little video here.
Today we're going to use our PET simulation to look at the relationship between frequency and wavelength and see if frequency and wavelength affect the velocity of the wave at all. You might be surprised by some of the results. First of all, we'll start by oscillating the end. Again, we're creating a transverse wave. You can see that the disturbance is perpendicular to the direction of the wave is traveling. And once again, we'll turn off the damping. So we don't want any friction to be occurring. We want a nice, clean wave that we can study easily traveling through the window. Again, we choose the windows that does not reflect and come back on its own. We just want to look at the effects the frequency has on wavelength. So up top you see a slider that gives us our controls over frequency. I can turn it to low frequency or high frequency. You can ignore the number. The number 50 does not mean 50 hertz. 50 hertz would mean that the wave is being created 50 times per second, and clearly that's not true. In this simulation, the 50 just represents the fact that it's at 50% capacity. That would be 100% capacity up at this end. So we can adjust the frequency of the oscillations by moving that slider. So let's start with a low frequency wave. And you can see right away when I create a nice low frequency wave, very few waves per second, the wavelength is quite long. And if I create a higher frequency wave, more waves per second, it in turn creates shorter waves. The wavelength gets smaller. Now, if I choose a frequency of, let's pick 20. Okay, so there's a frequency of 20, and I'm going to pause it. I'll step it through so we see one full wave, 2 crests. Now I'll grab a ruler, and with a frequency of 20, from crest to crest is one wavelength, and we can see that it's roughly 80 centimeters. From here to here is roughly 80 centimeters. Now let's take our frequency and double it. Let's bring it up to 40 and see what happens.
At this frequency, correct?
As the frequency increases, right?
What Greek letter is that?
Y.
Delta?
Alpha, omega.
Lambda. It's a lambda, right, Brian?
Yes, it's lambda.
Right? So that's the frequency. That's the wavelength. What was our wavelength yesterday when we did that handout? 360.
Okay, so I've doubled the frequency. Again, I'll pause it and measure from crest to crest. And we can see that our wavelength is now 40. So doubling the frequency is half the wavelength. It seems to be an inverse relation. Now,
I didn't touch anything.
I got the decimal point. For which one? But that's because you're doing this guy.
I hate
That's
DCs.
probably right. Which one? Let me see.
Max. Still going. The volume.
What happened to the sound?
let's bring it up to many waves per second. And then
Mute.
I didn't touch anything.
Oh, no, you muted.
You did.
For E?
How do you do that? 64 over 5.
Huh. Now it's not muted.
Check the connection.
That's an idea. Power for the speakers is in. Light on. Light is on. Okay. Let's just try another video and see what happens. Right? Try this one. Okay, so now my sound. When life keeps running, next thing I was brought, so that's actually. This is those speakers.
Oh, or is that what 4.2 is in the front?
The Lego movie. Go out and pay your money.
So, we're Marines.
Yeah.
We don't retreat, we improvise.
Is this gonna be lunch time?
So now, Miss Engelhardt, what you see right now could be a slight bit, but hopefully it will make sense.
So from this, from the answer that we got for each number, subtract 6.
Yes, you're trying to find the distance between the fingers. So in other words, you wish to know how far you have to move your fingers.
I do too.
Everything was going fine, and then it just stopped.
It's a short chair back here.
All the time, he's good. No, he's good. I know it's God is good all the time and all the time.
So, like yesterday's discussion, Ms. Curtis, I don't think you want to be seen on film wearing a hat. As far as yesterday's discussion is concerned, what do waves do that the other 12 basic functions don't do?
They're repeat.
Thank you. They repeat. So in other words, we have to develop some type of mathematics in order to describe something that repeats. What am I spinning right now?
One of those little thingies.
Oh, come on, don't think too hard. It's a wheel, it's a circle, right? And so you think about it this way, like the ancients did, the earth at the center, the sun going around the earth in a circle. Really? Oh, we're good again? What does every click represent?
3 feet or 1 meter.
Every click represents 1 full rotation.
Just 3 feet.
So in order to develop a type of mathematics that repeats, let's start with a circle. Thank you, bro. It's been nice having grad students who know more math than you do. Take a look at this picture. So Rachel Engelhardt, is this a little bit overwhelming the first time you see it?
No, it's not overwhelming, but it's just going to that first point.
Okay. What is different about this circle than the waves we looked at yesterday? What was the, oh, Josiah. What was the period of the graphs yesterday? It was 360. So 360, it went from 0 to 360, the wave went up and down, and it started again. 1 period, 1 cycle. Pass that back. Where are the angles now? Where are the angles now? You see the 0?
Yeah.
Let's all agree now that we have to start our angles in the same place. So let's start our angles out here. Is that okay? X-axis, Y-axis, so we're going to start angles here. Now if I was back in my room, I'd pull out my globe, but does anybody remember clockwise is negative, counterclockwise is positive? Why is that? I wish I had my globe. It's over in my room. Because if you take a look at the North Pole, the Earth rotates counterclockwise.
I know.
I thought you said.
So what's that angle right there? 30 degrees. 30 degrees. We're going counterclockwise for positive. Let's take a look at that right there.
Square root of 3/2 is the x coordinate.
Okay,
And 1/2 is the y.
good.
So
What
the
is the
angle that is 30 degrees corresponds to that point.
You told us to take 60 and subtract it from.
close? Very close. That was Olaf. You just impressed me greatly. Okay? So first of all, let's go back to the worksheet that some of you are working on right now. Who came up, hey Naomi, who came up with our musical scale? It's on the handout, 8-1, multicultural activity. Who came up with the musical scale? Pythagoras. What else did Pythagoras come up with? The Pythagorean theorem. Did he? No, he stole it from the Egyptians. But that's another story. But if we're going to talk about the Pythagorean theorem, don't we need a, what type of triangle? A right triangle. So here, let me come up here, and I'm going to drop that down. There's my right triangle. Do we know anything about that right triangle? Okay, it is a 30-69. You remember that in your OGT, right? So this is 30 degrees. Let's see, what do you call this side of the
Nice.
It's so hard. It's so hard to teach this way. Does anybody know what the length of the hypotenuse is?
A squared plus B squared equals C squared.
Let's see. Somebody said this, A squared plus B squared equals C squared. C is the hypotenuse, correct?
Yes.
Like in 10 seconds.
All right. Does anybody know what the length of the hypotenuse is?
B squared minus A squared equals B squared.
What is this circle called? What is the circle called? The unit circle. What's a unit?
One.
What's the radius of the circle? 1. What's the hypotenuse? 1. What is the length? Olaf has already seen this. What is the length of that side?
Half.
Isn't that the x coordinate and that's the y coordinate? What's the length of that side? Square root of 3 over 2. What's the length of that side? 1/2. What's going to happen when I put those numbers in for A and B? Let's see. Square root of 3 over 2 squared plus 1/2 squared. What's that going to have to equal? It's going to have to equal 1 squared. Do you believe me? Let's see. Yeah, you might want to write this down. Am I allowed to split up that squaring over the top and the bottom? Yeah. What's the square root of 3 squared? 3. What's 2 squared? 4. 4. What's 1 squared over 2 squared? Does that work for every one of those pairs on that circle?
Yeah.
Yes. Does that work for every one of those pairs? Jake, does that work for every one of those pairs on that circle? Thank you. Yes. What am I trying to get you at? What am I trying to get you to do? Why are we studying this circle? What do circles do that waves do? They repeat. How can we get, now this is the next part here, how can we get from the circle to the waves?
You cut it in half.
Somebody tried to do that yesterday. So here, group. If I take the circle and I cut it in half, and I cut it in half, is that the wave? No. No, it's not. Because those sides go vertical. That's a common misconception. You can check my lessons, right? So now, here's what you have to do. I give you a grid on the bottom. Come through the middle of the grid. And then go like this. Think back to the worksheet from yesterday. What? Oh. maybe I need to refine that. I'm gonna do this. Y-axis should go through there. That's why I'm doing this. What are we gonna put out the x-axis?
Sine,
What did we do yesterday?
sine, cosine, sine. Yeah.
What was yesterday? The x-axis was
The degree.
the degree. 360. What do you want to count by? Oh, I don't know. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. What do you want to count by?
100.
30.
I'm just kidding,
I didn't look at that last.
No.
There's
90.
no one single answer.
Just count by 30.
75. I won. Yes, he gets a 360.
I don't know. Count by 15?
Nice and
Is that going to be enough? 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360 there. Okay, now, let's start first of all by, now, wait a second. Go back and take a look at the unit circle. How many things are going on that unit circle?
10.
There's an angle, there's an x coordinate, and there's a y coordinate. So let me come over here. Let me put the angle, and in order to not get confused, let's use that symbol. Thank you, remember that from geometry. Theta. And let's take a look at the x coordinate. So in other words, I'm going to treat the x-axis as the angle, but I'm going to graph the x coordinate as the y coordinate.
Yes, and then you're going to use the dot control.
You want to come up and do it? Okay. That's fine. So here. 0 degrees. What's the x coordinate? Take a look at your unit circle.
30.
1.
1.
It's 1. At 30 degrees, it's the square root of 3 over 2. What about 45 degrees? Square root of 2 over 2. Is 45 degrees on here?
No. But somewhere.
It's halfway between 30 and 60. 60 degrees.
We're talking about that.
Oh,
1 half. And 90 degrees. 0. Let's see what happens. 1, 2, 3, 4, 5, 6, 7, 8. I gotta redo it. Right? I gotta make it nice. Yeah. So what do you want to count by? 0.25, 0.5, 0.75, 1. Did I? 0.25, 0.5, 0.75. Oh, I missed it. Gee whiz, Brian, I'm glad you're here.
Well, also Sunday, I found that I had a second. Yeah, so then Mom said we go on Friday. My cousin was leaving.
Let me switch colors now. let's see. 0, 1. Square root of 3 over 2. 0.866. That's approximately 0.866. Uh-oh. It's a little bit of error, right? So at 30.866, go there. Square root of 2 over 2. 0.707. 0.707. 60 degrees. Oh, I missed it. 45. 60 degrees. 1/2. Is that a straight line? No. 90. Oh, I forgot my 60. I got it. Oh, I wish I could do that better. What's going to happen now? Ooh! Oh! It works. Say that a little bit louder. A little bit louder.
It's gonna be cosine.
Oh, it's going to be the cosine. It's not going to be like the top half of the circle and the bottom half of the circle. It's going to be a nice, smooth transition. Now what's going to happen over on this graph? Smart, Alec. Now on the second graph, you put the angle out here, but then you graph the y coordinate. There's 3 things going on in the graph, and what you're doing is you're isolating 2 of them. The angle's going around the circle counterclockwise. But you're taking that thing that's going around the circle and you're actually treating it as a x-coordinate. Anybody confused?
Yeah.
You've been graphing x's and y's all the time, right?
Now we gotta do Z.
A z is more of a 3-dimensional.
Yeah, that's not fair. Oh, wait,
Well, what you're doing is you're looking at a circle where there's 3 things going on, and you're isolating them 2 at a time. It would be really cool to graph it for you. Is there some way that you can use this information to do this? Take a look at your unit circle. Is there a relationship between what's going on with the x-coordinates and the y-coordinates?
Yeah.
What do you see?
That the y is negative.
Okay, let's just focus for, oh, here, let me review this. This is the first quadrant. What's this quadrant? Second quadrant. So I'm going counterclockwise. Third quadrant. Fourth quadrant. Over here. The first thing that you have to keep in mind, what defines the x-coordinate and the y-coordinate? Who defines what the x coordinate is and what the y coordinate is? Jay, you're making me look really bad. What defines the x coordinate and the y coordinate? Who decides what to put on the x coordinate and what to put on the y coordinate? So can I put anything on the x coordinate I want? And anything on the y coordinate I want? As long as I let you know what it is. So we decided to put the angle on the x coordinate and then the y coordinate on the y coordinate for the second graph and the x coordinate on the y coordinate for the first graph. And then what am I trying to get here?
Then I was trying to yeah, reasonable.
What? How do you get this function?
Like I was pissed yesterday, but I was happy they told me like, hey, like that, but I was pissed.
Do you need a tool that's going to describe things that are repeating? Yes. So you start with what nature provides you with. Where does that wave come from? Is it half a circle here and half a circle there? No. No. Misconception. Not going to happen. So what is it? If OGT wasn't going on, I'd take you guys out to the hallway and do this. And I think the only open space we have over there, so I need a couple volunteers. I got flowers and all out. Head back over there.
What I'm gonna do is good luck.
Take that in. Anybody want to come to sing? Not just a slinky, but a super slinky. No, you're not jumping, Olaf.
I would be the one who's jumping.
Hold that against the floor, Olaf. Grab that. Hold that against the floor. Flowers, hold it against the floor. Now, Olaf, give it a little boom. A little flick.
Flick it.
Here. Try it this way, Olaf.
Oh, up and down. Oh, like that.
Wait, you're not supposed to do it too.
Okay, Olaf, go ahead. Oh, man, put something behind it there.
What?
Is Mishan moving? No, you want to move?
Can I?
Yes, go
Yeah, the
ahead.
impulse move.
Breathe, can you
breathe,
get
breathe through it.
Can you get what is known as a standing wave? Ooh. Uh-huh.
This is great.
Go faster. Ah. Okay, now stop. Olaf, just give it one flick. Oh, come on. Ooh, we bounced back. Go ahead. Ooh. Okay, now I want you both flick it at the same time once.
And one time. Oh,
Ooh.
interesting.
I'm sorry my calculus students messed that up there. So, wave, standing wave. Standing wave, go ahead. No, 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 no. Standing means it's go, go, go. You're both doing it at the same time. And so when you look at it, it doesn't really look like it's moving.
Not at all.
Looks like it's flipping back and forth.
Uh-huh. Is that a sine wave or a cosine wave?
Cosine.
It's a side. Where does it start?
No, wait.
Well, we can't tell.
No.
We don't know what's coming from the origin.
Is it a sine wave or a cosine wave?
Wait, it's a,
When do you start?
no, it's a cosine wave because like it's starting at one.
Is it both at the same time?
Yeah.
Oh.
No.
Okay, is class over now because we don't have bells?
Yeah.
Okay. Thank you.